All right. So let's get started. As usual, I'll review the previous lecture, and if there are questions, ask as we do the review. So today we're going to start a new section of this course. We're going to be talking about standard model of particle physics for 2-3 lectures, probably 3 lectures. And what we're going to cover today is the particle content of standard model, right? So it's perhaps the most important theory, interacting quantum field theory in 4 dimensions. You should know about, you should learn about, and it has a lot of details. So there's like lots of different particles. There are symmetry. There's a gauge. It's a gauge theory, non-abelian gauge theory. So we're going to go over the matter content of it today. Then we're going to discuss Lagrangian interactions and all of that, the symmetries in the next lecture, and probably a whole bunch of various subtleties of it in lecture 3. We'll see how things go. All right. So last lecture, we were discussing the quantization of spontaneous symmetry broken gauge theories, the Higgs mechanism. Recall that the Higgs mechanism could be understood as the statement that in when you have spontaneous symmetry breaking gauge theories, you end up with massive vector gauge bosons, right? And that's called Higgs. And this is the setup where you give there is a scalar field, or there's some fields coupled to the gauge field. They acquire 1-point function, and then part of those degrees of freedom are eaten by the massive gauge field. The remainder is the Higgs. So the spectrum around the vacuum, the new vacuum, right, contains massive gauge boson, and this is consistent with gauge invariance, in parentheses, word identities. We saw that in global spontaneous symmetry, in spontaneous symmetry breaking of global symmetries, we ended up with Goldstone bosons. There were no Goldstone bosons for gauge theories, spontaneous symmetry breaking of gauge invariance. And what we ended up was a massive vector field. This is the phenomenology of it, right? The particle content at low energies. All right. So we reviewed the quantization. We discussed the quantization. I'm going to review the same material, but focusing on SU2, because that's going to be important in standard model, right? So here's the Lagrangian. There's the SU2 non-abelian gauge theory. There are the matter fields. These are charged, and they transform in the 2-dimensional representation of SU2, fundamental, right? And then this representation is adjoint. Oh, let me change the notation. All right, so I have 3 gauge bosons, A mu A, right? And the gauge invariance, gauge transformations are like this. Notice that because we're talking SU2, the adjoint representation, these FABCs are just epsilon tensor. The totally antisymmetric tensor. The two-dimensional representation of SU2, this is a fundamental representation. These representation matrices are half tau of A, where tau of A are just the Pauli matrices. So here, the Higgs is a complex scalar field, which is an SU2 doublet, right? The transformation of the scalar field under an SU2 transformation, gauge transformation, is this way, and here's your covariant derivative, which will include an interaction with the non-abelian gauge field. Good. So to discuss spontaneous symmetry breaking, we want to give VEV, vacuum expectation value, to phi j, right? So here it is. This is a vacuum expectation value, and this is a fluctuating field, and we're going to set the vacuum expectation value of the non-abelian gauge field to 0. Sorry. In the expand, yeah.
We set the vacuum expectation value A to be non-zero.
So that becomes the issue. Yeah, that's a very that's a pretty long discussion. There's a lot of interesting physics associated with that. But previously, we used that as a quick and dirty way of calculating effective action, beta functions using effective action, right? So we use that as a method. And the key idea was that if you give vacuum expectation value VEV to A mu of A's, the resulting functional effective action will have to be invariant under background gauge transformation, and that was very constraining, right? But we haven't discussed the physics of it, and we won't discuss it. But for one thing, you already know that if you give vacuum expectation value to a vector field, you have done something crazy, right? What symmetry have you broken? Yeah. Whereas for a scalar field, it's okay. Maybe you broke a Z2 symmetry, phi going to minus phi. It's no big deal. But breaking Lorentz invariance, well, I mean, it's a vacuum that's not Lorentz invariance. It's something violent. So it's something very special. All right. There are a lot of setups where Poincare transformations are broken, right? What's the simplest setup? Finite temperature quantum field theory, right? It's a setup where Poincare invariance is broken. Okay. An expansion of d mu, the covariant derivative phi j, the kinetic term, the covariant kinetic term for the Higgs field, we found this interaction vertex, right? This is the interaction vertex that mixes had the kinetic term, the second order term, which mixes A mu of A, the gauge field, right, with the certain components of phi, the fluctuating field, right? This is the non-abelian analog of the same mixing term we found in abelian gauge theory, right? Where phi2 we called it, right? That Goldstone mode was coupled to A mu. Here's the same story. And then we said this is inconvenient to deal with. A good way to go around this is to use gauge fixing, a choice of a gauge fixing, that's our strategy, to remove the mixing term. What was that choice? This was precisely the choice that we picked. And we showed that this choice is engineered. Well, the choice of the gauge field, this is the gauge fixing condition. But we picked the omega of A to depend on the fluctuating field, on the scalar field. And we made the following choice, and we showed that this choice is precisely the right one that cancels this annoying mixing term. But then there was a cost that we paid. This gauge fixing choice comes with introduces ghosts because it involves the determinant of when we introduce this gauge fixing in Faddeev-Popov, we integrate over different choices of gauge with Gaussian weight. There was a determinant that we picked up from the change of variable, from the change of the measure in the path integral. So I'm gonna go over that again. So here's the choice, right? 1 over 2c my g of a squared. And now you can see how it's actually helping. There is a term which is like 1 over c d mu a mu squared. There is a term that's c omega a squared, right? That will actually give a mass term. Well, you've seen that. And then there is a diagonal term, which is c independent, and it's been tuned to cancel that propagator. And the way that works is that here you have phi naught, phi 0, right? And then this is del mu a mu nu. That is precisely the structure you need to generate, the structure you need to generate this term. Good? All right. So this term actually gives a mass gauge dependent, C dependent mass term for the Goldstone mode. And we also argued that that's actually every time you say something like that, you instantly realize that this Goldstone mode is unphysical. Because if it's up to me to decide what the mass is, I'm just gonna pick it to be infinite. So it just simply doesn't fluctuate. All right, here's the kinetic term. Remember that the C was introduced as because we wanted to invert the propagator. This is the RC gauge. To invert the kinetic term to get the propagator. Yeah.
Yeah, when you did that, we could also take the choice of C equal to 0, right? It was Feynman gauge or something. But
yeah.
Here in the above line which you showed, if we take like in the previous slide which you showed, if you take C equal to 0, then there will be no mass term for the gold storm, right?
Yeah, but there are other issues over there. So, the other issue is that there's a C here.
Yeah.
Right? So the transverse case, actually, sorry. Where is it? Where is my propagator? Well, okay, sorry. Well, all right. So this is the kinetic term we're dealing with. There is a mass matrix we introduced for these are the masses, right? This is the mass matrix that we obtained for a mu for our gauge field, right? There's a mass matrix associated to the gauge boson propagator, right? Which depends on the gauge coupling and the expectation value, the rev of the scalar field, right?
Is the mass of it as an equivalent?
No. No. It's TATB. It's a matrix, yeah. We're not taking the trace, right? That's if it were diagonal, I wouldn't have put -1s here. So to find the propagator, what you need to do is you need to invert this for general C. This is invertible, and here it is. This is the propagator, and this is the matrix. So these are matrix inverses, right? Now, the poles of the propagator occur at physical masses. These are the eigenvalues of M squared, right? So the physical mass is precisely the eigenvalues of those guys, but M is not the eigenvalue. M squares are not the eigenvalue. Good? All right. Am I going too fast? All right. So there's a unitary gauge, C equal infinity. In this gauge, the Goldstone boson is infinitely massive. It just drops from the spectrum, and you get the following propagator. There is a Landau gauge, C equals 0. This is a transverse one, right? And it looks like what you would expect from, we work with the transverse gauge for a while, right? And then there's a Feynman gauge where everything is just proportional to eta mu nu. We just drop the p mu term, right? So these are gauges you could work with, but they're all inside RC gauge. All right, any questions? Now, the standard Faddeev Popov with this gauge choice gives ghost even for the abelian theory, right? For the SU2 that we are calculating, this was our gauge choice. I have to vary it with respect to my gauge alpha b, gauge transformation. I obtain 1/g del mu d mu ab. This part has a p which is del mu, right? That term appears in QED as well, but that term is independent of all the fields. So it's just an overall constant. You could just drop it, right? Just ignore it. But now, because this is covariant derivative, and for the gauge field, there's FABC appearing there, right? And in our case, epsilon ABC, right? So this is no longer trivial. It actually depends on the gauge field. And when we exponentiate this, write it as an integral over ghost, the log of this determinant as an integral over ghost, you end up with a coupling between the ghost field, ghost anti-ghost, and the gauge boson. Now from RC gauge, you also obtain a coupling between the Higgs particle, right? Our Higgs, the fluctuating mode, and the and the gauge and the ghost anti-ghost, right? And this part of it survives in the abelian theory as well. So spontaneous symmetry broken gauge abelian gauge theory will have a ghost sector where ghost is coupled to the Higgs. That was the one key difference, right? And this is the price we paid to get rid of that this mixing.
Not that.
Yes. This is the price we paid to get rid of this mixing. Good. All right. So as you do for Diopopov, next to these terms that we had in the Lagrangian, where are they? Yeah, we had these terms in the Lagrangian. Next to it, we're gonna end up with the ghost terms, right? So I'm gonna just we showed the Feynman diagram, the propagators, right? There are interactions. I trust you guys, you can write them down, but here are the Feynman diagrams for the propagators. There's the gauge field propagator, there's the Higgs field propagator, and the ghost field propagator. Here, what is important to notice is that there is some matrix. Oh, hopefully this notation is not confusing. Here, this m squared is coming from the second derivative, the curvature of the potential of the scalar field, right? So this is model dependent, right? And now the other mass matrix, so there are two mass matrices that work, right? The other mass matrix that we're discussing is related to this FAIs, right? They're coming from the fact that you have vacuum expectation values, right? So if you didn't even have spontaneous symmetry breaking, you would still have this m squared. That's why I ignored it all up until now. But now here I'm using this notation where I'm writing everything in terms of FF transpose, right? Or F transpose F. I think this is wrong. I think this should be FF transpose. Yeah. Okay, so here are the propagators. I trust you guys can write down the vertices, and we're gonna do the vertices actually when we discuss the electroweak. So as an example, we're gonna work out the electroweak within Standard-Model particle physics. All right, any questions? It's a natural moment to pause because we're gonna go to the next section and start talking about Standard-Model.
We haven't discussed the beta functions.
So that is correct, right? But the beta function, when you break when you go through spontaneous symmetry breaking, what you have done is you have you're looking at very, very low energies, right? So you have a potential. You're looking at the minimum, very, very low energies, and in the low energy processes, things change, right? But at very, very high energy, the theory is unchanged, right? When you, like, for example, when you were discussing QCD, right? Beta function of QCD ending up the theory ending up having asymptotic freedom has to do with the deep in the UV behavior. And deep in the UV, the symmetry is restored, right? Deep in the UV, you don't care about the vacuum, right? Like you have so much energy that this potential, you're just like, don't feel the minimum of the potential, right? You just have
Everything is like a simple.
yeah, like you have just so much energy that you just never settle to this vacuum versus that vacuum, right? So all these the spontaneous symmetry breaking thing I haven't discussed, we might discuss it, is that, well, you know already from StatMech that it's a low energy phenomenon, right? As you look at the low energy, you end up with spontaneous symmetry breaking. At very high energies, physics is unchanged. But you could calculate beta functions, you could do all sorts of calculations, like if you were to do this actually, that simplest way would be the effective action, right? The effective action would be the simplest way, because you already know actually the beta functions here are just at one loop are decided by kinematics, right? We wrote down precisely well, actually, you gotta be a little bit careful because now your vector field is massive, your gauge field is massive, so you go through the kinematics of that and you find it.
But
Yes.
there are only conceptual ideas of it, so say again, you have to repeat the same procedure we used for the previous things and it should be possible to get it.
So the whole point is that none of Abelian gauge theories gave us genuinely interacting theories in the infrared, right? And they involve massless gauge bosons. Spontaneous symmetry breaking was a setup where you're still working in that well-defined theory, but you're exploring different vacuum of it. Right? So in a sense, you're guaranteed that it's still an interacting theory. Right? You're just exploring different vacuum. But you could do these calculations.
The reason I was asking because when we're talking, for example, FIFO theory.
Yeah.
We've seen that it is like marginally irrelevant.
Correct.
FIFO theory. So and in DC4. So so I was wondering that when you couple it with these non-abelian gauge fields, they help it become marginally relevant or relevant.
Oh, okay.
That is the question.
Very, very, very good.
That is
Okay, actually, there's a homework I was writing today, that's related to this, is that, you will see in standard model particle physics, U1 in 4 dimensions, like QED, in 4 dimensions is not well behaved, right? It has lambda, I'll pull in the IR, right? Whereas SU2 times U1 times SU3 is okay, right? And the reason is that at one loop, when you do these calculations, there's a contribution coming from, or even more physically, we could compare them as screening versus anti-screening, right? And it's all about the coefficients, which one is bigger, right? It's about the number of fermions that run in the loops. So it's a competition between the numbers, and you could arrange not always, but like if you play with the parameters at one loop, quite often you could arrange for quantum field theories that are asymptotically free. The crucial idea was that at one loop, all of these are just like counting, right? Any other questions? All right. Okay, we're gonna change gears completely and we're gonna introduce and discuss the standard model of particle physics. So today I'm just gonna go over the particle content, but before doing that, I want to remind you guys of fermions, representation theory of spin half particles, and 4 dimensions. It was a little bit involved, went through this in gory detail in part 1 of the course. So I just want to remind you of the basic minimum that you need to have like as working in your working memory. All right. So in 3 + 1 dimensions, we said that we constructed the representations of the Poincare group using gamma matrices, right? You recall that. And then we discussed spin half representation as Dirac spinners, right? These are 4 component spinners, like Sig1, C2, Chi1, Chi2. And under a Poincare transformation, they transform in the following way. Or Lorentz transformation, they'll transform in the following way, right? And if you recall, we wrote explicitly what these Lorentz transformation matrices are. These are unitary transformations, right? And the generators of them, we repackage them in terms of JK and KK, right? Do you remember the Lie algebra structure of this? 2 copies of SU2. Here's 1 copy, here's another. Well, actually, no. It was JK plus IKK was 1 copy, and the other one was like that. There are 2 copies of it.
They're a bit mixed.
Yeah. So aside representation theory, but here when we're discussing spinners in 4 dimensions, we noticed that these Lie algebra things, these Lie algebra guys, are diagonal, block diagonal, right? Which immediately told us that when we have these fermions, Dirac spinners, if I don't have a master, right, the guys above and the guys below won't talk to each other under Lorentz transform, Poincare transformations. Je won't mix, right? So this was the notion of a particle. We advocated the idea that the notion of particle is something that is a state that you could just apply Poincare transformations and it will be moving within the same representation. So it's an irreducible representation of the Poincare group, right? That was what the particle was. So by that logic, I can think of Dirac spinner, if it's massless, as two particles, right? And we gave them names. We called them Weil spinners, or sometimes we call them Majorana spinners. I'm just going to review that story. So this 4 vector has the 2 components above and 2 components below, of course, in this basis, right? Won't mix. The representation is reducible, it's block diagonal. So we can cook up projections to the guy above or projections to the guy below. And that the way we do that is using the gamma 5 matrix, right? Identity minus identity, and this is the projection, right? So it gives you Xi or Chi. These are Weil spinners. They have 2 degrees of freedom. They're complex. Right? Now, to introduce Majorana spinners, we notice the following. If psi L is a Weil spinner, epsilon is the following 2x2 matrix, epsilon psi L star. If psi L was left-handed, epsilon psi left star is right-handed, right? So, which means that it's a little bit of a matter of choice. I can represent the same 2 degrees of freedom in the following way: Xi and epsilon Xi star. These are called Majorana spinners, right? It's still 2 degrees of freedom, right? It's still 2 degrees of freedom. And in a sense, whether we use Majorana fermions or Weil fermions to formulate the theory is a matter of choice, right? We'll see that I'll use the formulate. We'll see that actually standard model particle physics is a lot easier to formulate using Majorana fermions, but because you work with Weil fermions, it won't matter.
Is there any physical relevance for switching between these 2 degrees of freedom?
Basis.
That's it, nothing.
Basis, yeah. The action of Poincare transformations are nicer in the Majorana once you expand in terms of Majorana spin. Right, but you could work with Weil fermions as well. Okay, so sometimes when you pick textbooks on standard model, they will tell you the particle content is here are the Weil fermions, right? But then as they start writing down the transformation, they talk about spinners, Majorana spinners, right? So I'll try to clarify that very clearly. All right. So we're good. Representation theory. We know what Dirac spinner is. Majorana, a Weil fermion is spinner. Spin statistics. Hopefully you recall that as well. It tells you that what does it tell you? If you are the half spin particles are their statistics is anti-commuting. All right. So they're fermions. Okay. Here it is. Standard model of particle physics. We start with the gauge sector. Actually, let me not even mention that. Thanks. So I'm gonna describe to you. Are there any questions here? It's probably I should pause. Are there any questions? So actually, what I will do the following. If I have this is psi left, right? This is a Weil fermion, left-handed Weil fermion. Is that good? I'm gonna introduce this thing, which is C star, C star, and I'm gonna call this left-handed Majorana fermion. Is that convention clear? Right? This is a left-handed Majorana fermion, still 2 degrees of freedom, but I'm just gonna copy this guy in here. Or to simplify my life. All right. So this is still I write this Majorana psi of M. but it's still left-handed. I'm gonna call this left-handed. What is a right-handed Majorana fermion? The right-handed Majorana fermion, I don't know what to call it, the right-handed one, left-handed one, would be high. Oh, I forget here what I had to put. There was another combination of epsilon that I had to put here, right? So then you immediately realize that if I start with a Dirac spinner, I can, in 4 dimensions, I can think of it as 2 Majorana fermions, right? And that's precisely what we're gonna do. We're gonna think of electron as 2 Majorana fermions.
It's all a matter of how we split up the depth.
Precisely. All right. Yes,
Two spin within the same representation space.
say it again.
These two spin within the same representation.
So, the representation theory that I introduced for this Dirac fermion, if it's massless, is reducible, right? And the top and the top component and the bottom components, they are in 2 equivalent. I should call that equivalent, in 2 different irreducible representations, right? So of course you could embed them. It depends what you mean by representation space. If you mean they're of course living in the same 4-dimensional reducible representation, but you could view them as ERAPs separately.
To remember the Majorana spin within the real representations.
Yeah, so when we talk about reality, it's about this guy being related to C star. Right, that's it. Well, we discussed. I suggest that you read that. We went through this in absolute gory detail in part of the course. So the notes are notes, and we can go over them. Yeah.
This is like deviation, it's Suzy, for each of the quarks or the particles, we have some associated particles, right? So do we use the same representation for them as well?
Supersymmetry representation theory is different because it's space-time symmetry. So you gotta redo everything from scratch. Yeah, it's a different story. But laws are the same, right? Like you have a bunch of EREPs are your particles. Your particles are EREPs. So the statements that you're talking, like always think about it this way. The Poincare group, if you're talking about spin half representation, it's very much spin dimension dependent. Even dimension and odd dimensions are different, right? So you got to go through them case by case. We're discussing 4 dimension. In the previous part of the course, we discussed 2-dimensional, 3-dimensional representations as well. Here we're going through only 4 dimensions, and the 4 dimensions. This is what a Majorana spinner is. It has 2 degrees of freedom. Here's what a Weyl spinner is, and you know what a Dirac spinner is, right? So that's at least within the context of 4 dimensions. Let's just go with these definitions. Okay. Good. Any other questions? All right. So that was a very brief recap of what spin half representations are. Now let's just forget about that for a second and talk about the gauge sector. Here's the important part. Standard-model particle physics is a quantum field theory. It's genuinely interacting in 4 dimensions, so it's an interacting theory. So it's better be renormalizable, have the right beta functions, blah blah blah. It describes 3 of the 4 forces we know in nature: strong nuclear force, weak nuclear force, and electromagnetism. Strong nuclear force is described by a gauge theory that we call is SU3, but we call it SU3C, C as the color, right? So color is like strong force charge. Anything that has color is interacting with strong force, true strong force. SU2 left, this L is left. That's very important because we're going to have left movers, right movers. They're going to transform in different representations, right? So this is SU2 left times U1Y, Y for hypercharge. This SU2 left times U1Y is called the electroweak. It's a unified, it's a theory, it's a gauge theory that unifies electromagnetism and the weak force. This U1, importantly, is not the electromagnetism U1. Very, very important. This U1 is not the electromagnetism U1. We're going to go through this in detail. What's happening is we have a Higgs particle that is charged under SU2 left times U1Y. It gets a VEV, it spontaneously breaks SU2 left times U1Y down to a U1 electromagnetism, but this U1 is not this U1. It's a different U1 subgroup. Good? We're going to go through that. But it's important, the hypercharge is not electric charge. Okay? All right, so that's what we mean by electroweak. When we say electroweak, we mean SU2 left times U1 of Y. But electroweak is not something times electromagnetism, right? Electromagnetism sits inside it. Okay, so these are all in adjoint representation. So what are the gauge bosons? The gauge bosons are of SU3, we're going to call them gluons, right? They're vector fields, and there are 8 of them. Why 8? The adjoint representation of SU3 is 8-dimensional. SU2 left, there are 3 of them, W mu A's, right? Up until now, I was calling all of these categorically A mu A, right? But now I want to distinguish between them. These are gluon, hence G. This is W because it's weak. I don't know. I don't have a better way of writing things down. And then this is B mu. This is the gauge field associated to the hypercharge. It's not the photon, right? It's not the photon. All right. This is 8 spin 1 particle. This is 3 spin 1 particle. This is 1 spin 1 particle. They're all massless so far, based on what I've described. Right? So you know how many degrees of freedom do you have? You have, right? Do you know how many degrees of freedom? So spin 1 massless mode. How many degrees of freedom do you have? In 4 dimensions, you have 2. 2 polarization. There are 8 of these guys, 3 of these guys, and 1 of these guys, if you do the count. The gluons have color. Whatever they call they couple to is interacting through strong force. Here, L is because these W's, these spin 1 particles of SU2, couple to only the left-handed Majorana fermions. Only the left-handed Majorana fermions, not the right-handed ones. Good?
Is there a matter of convention or is it?
Sorry?
Is there a matter of convention that is left-handed or?
Well, I mean, well, it depends what you mean. Are you talking about Majorana versus Wild? That is a convention.
I'm talking about why are we, why does it couple to only left-handed?
Just fact.
Experimental.
Yes.
That is the reason why you find only one-handed neutrinos, right?
Yeah. Well, I mean, it's not the reason. We're describing the fact that we find only left-handed neutrinos. Right? So electron, we're going to go through that. As a Dirac fermion, will be comprised of left-handed Majorana, right-handed Majorana. Only the left-handed Majorana interacts with electroweak. The right-handed doesn't. Good? The same for all the other particles. We'll go through. Hence the left-handed. So that's like it's something that we haven't discussed much, chirality. Right? So chiral symmetry breaking, all of that, we're going to go through that in detail. And that's what anomaly comes in. Those are good examples. I've delayed this up until now. Because I wanted to give you an example of physically motivated theory where there is chirality. All right. And this Y is hypercharged. It's not the electric charge. But it's a U1, so it's just charge. Right? All right. So these were the gauge fields. What is the matter content? What is the content of stuff that are charged? Now I have to tell you what other matter content I have. First, I'm gonna call all my particles that are not talking through color, that are not coupled to strong force, as leptons. Right? So leptons by definitions, there are particles, they all spin half fermions, right? That are interacting not through strong force. So if I have to write down the representation theory of SU3C times SU2 left times UY of 1, and I'm gonna write it this way. This is a representation of this guy, this is a representation of this guy, whatever they are. Leptons by definition have trivial representation here. Right? Every time you see one here, it's a lepton. And if it's a lepton, there's one here. One means trivial representation, one dimension, right? Okay. So I'm going to explain the rest of the representations later, but this is the notation. Now, leptons, there's something really funny about Standard Model, that we have 3 generations, there's 3 copies, there's 3 families. So we're going to go through that. There are 6 leptons known today. There is electron, muon, and tau. There is neutrino electron, neutrino E, neutrino mu, neutrino tau. The fact that I'm telling you there are 3 generations, I'll already tell you also the labeling, tell you that E and neutrino E, mu and neutrino mu, and tau and neutrino tau sit together in some way. We're going to see how. And there are 3 generations. There are 3 of these guys. I'll collectively denote these guys by L. Every time I write L, it's a lepton, right? So for example, if I'm writing some sort of interaction term, L bar, L dot, 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 this is any lepton, the side bar type interaction. So that's notation. We're going to formulate Standard Model using Majorana notation. Good? Any questions about the leptons? So these are all the particles, there's 6 of them, that interact through electroweak, but not color, not gluons. Good? Now, hadrons are the rest of the particles. These are the particles that do participate in strong interactions. Right? So they do not have one. Now, there is like a zoo of hadrons. Hadrons are like tons of them. And you know why, actually? Yeah, precisely. Because QC, the SU3, or combined, like in the IR, the strong force is gonna get very, very strong, which means that you're gonna end up with these really, well, strongly coupled theories, right? And you're gonna have a lot of bound states, right? So you're gonna have a lot of emergent particles, right? New emergent degrees of freedom, effective particles. But at high energies, if you want to just classify them at high energies, where this is not very strong yet, everything is like, again, formulated in terms of 6 quarks. And I'm going to organize them again, like in terms of 3 generations. So DSB, down, strange, bottom, up, charm, top. Right? This is good. Okay, good. We're going to collectively denote them by Q. So I can write interaction terms Q, Q bar, da, da, da. Right? This means it's a hadron. This means it's a lepton. This means that this interaction, so this is nonsensical. Right? Because these are leptons, they can't sit with G. Whereas here, anything goes. Right? All right. So that's all the particles you need to know about. Well, awesome. So let's organize them right away in terms of 3 generations. So here are the leptons, and here are the hadrons. The generation label is M1, 2, 3. We're gonna call the neutrino of, oops. We're gonna call the neutrino of electron nu1, neutrino mu1, neutrino 2, and neutrino tau, neutrino 3, electron mu and tau, E1, E2, E3. Good. So these are the 6 leptons we had. Let's just label it. I want to use the minimum number of variables to write down, right?
Do the generations have some mathematical significance or it's just a level?
No, they definitely do. We'll get it. The hadrons, yeah.
You mentioned that the hadrons usually appear as bound states, so like these 6 quarks. And these are because they're interacting with the SU3 part. SU2 also is a non-abelian gas, right?
We'll see that. Yeah, we'll see that.
I was gonna ask whether
So you're asking whether electroweak exists as is asymptotically free. That's what you're asking. We'll get there. All right. Any other questions? So the hadrons, we're just gonna write them using U and up and down with labels M, right? So U1, U2, U3, up charm top, down strange bottom, right? So that I only need 4 letters, right? So I only have neutrinos. There are 3 generations of them, right? I have electrons, well, electron, muon, taus, right? EMs. These are the lepton content. And then the hadrons are going to be other content. Oh, U of M, B of M, right? Here's where things get a little bit funky. I have to introduce left-handed and right-handed notation. So I'll use cursive versus not cursive. Hopefully it will be visible. All right. So far so good. This is leptons, hadrons. I haven't given you the masses. I haven't given you any of those, but these are particles. They have masses. Blah blah blah. We'll discuss those later. Any questions?
I don't know if they discuss this further or not. Is there any mathematical reason as to given this model as to why there should only be 3 of them? Like
No, it's
this is just
an unsolved problem.
it's just like input experimental input that there should be
Correct.
3 electron neutron thingies, then 3.
That's all the particles we've seen. If tomorrow you find a new particle, you might have to come up with a 4th generation.
But it won't. So that my main part of the question was, it won't like irreversibly damage the bond. So
Well, I mean, no, you're asking whether it's easy to generalize the model to include a 4th generation, 5th generation. Absolutely. Now, having said that, there is like decades of phenomenology of what is called beyond standard model, looking into how physics could change, because this is all that we've seen up to 10 GeV, right? What if we push it further and discover a particle? Then let's add minimum. So there's like minimal, try to modify standard model minimally, right? And then there's like decades of physics. There's like a whole field called phenomenology that studies these questions, and there's tons of intuitions, right? But I would say this, except for 2 things, there are 2 issues within standard model particle physics, which sort of hint at new physics. Well, there are several things, but 2 of them are very direct. We're going to comment on them, right? But for the most part, except if you just like ignore about those issues, standard model particle physics could be the full story, right? It's a standalone theory. Now, if you just introduce a new particle, you'll have to think through how it couples to everything. And you might upset a bunch of theorists, right? Because they might not like it, because for other reasons, right? Because they're gonna run in the loops, right? They're gonna run in the loops. The issue being that, yeah, okay. I said what I said.
Another question.
Yeah.
Hadrons decouple directly?
Hadron, yeah. Well, remember the definitions. Hadrons are particles that talk through strong interactions. That's the definition. So I'm gonna give you the representations. All right, so as a baby step, let's just beat up electron. But you already know that this electron story I'm gonna tell is gonna be very generalized, right? So electron, I can think of it as while, right? Electron is a Dirac spinner. So I can think of it as E left, E right, as while fermions, but I'm not gonna. I'm gonna think of it as two copies of Majorana, right? Well, actually, I've written it. I don't know why I'm writing on the board. Two copies of Majorana. There is a left-handed Majorana, curly E of X, and then regular E of X. This is the left-handed Majorana, right? So E left, and I put the epsilon L star, E star down here. Oh, there was a minus sign that I was missing over there, right? So epsilon of R, and then this is the other Majorana. We're gonna call this the right-handed Majorana. We're gonna call this the left-handed Majorana, right? And of course, I can think of the Dirac spinner in this one.
And PR projection operators.
Yeah, projection to the top two, bottom two. One minus gamma 5 over 2. Right? Or simpler way of writing it. Identity minus identity. Right? This is gamma 5. So it's all this if you add. All right. So this is how we're going to decompose our electron, right? Left-handed electron, right-handed electron. Majorana. Okay, so now another thing. Let's just think about this for a second. These guys, these fields are going to transform in E-reps of, so the representation theory of U1 hypercharge is very obvious. It's always one-dimensional. It's an abelian group, right? It's just a charge. So I have to, but under the representation, under the SU2 left or SU3C, these guys transforms in E-reps. If I write a vector, it's either I'm viewing it as a vector of SU2 or vector of SU3. It's conventional, it's a lot easier to write vectors, these doublets or these representations of SU left 2. You could do the other way around. You could try to write them as like triplets. We're going to see the fundamental representation of the gauge boson. Sorry, of the gluons. But it's a lot more convenient to write them in terms of SU2. We're going to see why. Because both hadrons and leptons are naturally transforming under SU2 left, right? Whereas leptons don't talk to each other under SU3. Good. So here's what it is. I'm gonna take left-handed neutrino, PL of nu, put it next to PL of E in a doublet of SU2 left. This is not the four-dimensional vector, the vectors I was writing up until now. This is a representation of SU2 left. Right? Said differently, these are related to the A labels I was putting. Right? So I'm just realizing the A label as matrices. Keeping alpha labels as they are. And those are the only other labels I can. Right? Now, here are all the representations that are going to appear. The representation of this guy is going to be labeled, it's one-dimensional. It's going to be labeled by the hypercharge. I'm going to say that in a second. Right? That's the charge. Hypercharge associated with this. The fermions that we have, the leptons and hadrons that we have, are going to transform as fundamental representation of SU2. This is a two-dimensional representation, right? And here they're going to be 3 or 3 bar. right? That's it. That's all I've got. So far, so good. I'm gonna write these expressions as representations of my fermions, my leptons and hadrons, right? Of which I have these guys. I have my leptons and I have my hadrons, right? 6 of each. So 12 of them here. Good. And every time I write one in these representations, they just mean trivial. Except for, sorry, this is not, this is just charge, right? Hypercharge. So what is this hypercharge business? Well, this is let's say this is some sort of a spinner that has hypercharge Y. It means that under U1 hypercharge, it transforms in the following way. E to the power of I alpha x, Y, psi of x. Right? That's what hypercharge means. Good? All right. Here are my leptons, nu M and EM. One thing to know, I'm gonna, for neutrino leptons, I'm gonna take them to be only 1 Majorana. I'm not gonna take the right-handed Majorana neutrino. The right-handed Majorana neutrino could be added as a field, but then you realize that it will have to, with some consistency relation, it will have to transform as 1, 1, 0. So it's not coupled to anything. That's why we drop it. We're going to see that in a second. So for now, I'm describing you as fact. I mean, this is what we've seen. We've seen left-handed neutrinos. So I'm just going to have left-handed Majorana neutrinos. That's it. No right-handed ones. For EM, so that's neutrino M for all the 3 generations. I'm going to take that. For EM, electron, muon, tau, I'm going to take them to have 2 Majoranas, right? Left-handed and right-handed Majoranas. Is that good? And I'm going to write them as Curly EM and EM. So far, so good? Now, the hadrons, a lot easier. They have both Majoranas, left and right. Right? Curly U, Curly D, UM, EM. All right? I said this before. The thing is, you could add this right-handed Majorana neutrinos to standard model, but it turns out that it will have the following representation, which means that it's not going to talk to anybody, any of the gauge bosons. So it's not going to interact through a strong interactions. It's not going to interact through electroweak. So good luck seeing it. Everything does. But good luck detecting something for gravity. Also, especially this theory has no gravity. It's about all forces but gravity. Right? All right. Okay, here are the representations. The leptons and the hadrons. So I'm going to take, as I said before, I'm going to put neutrino left-handed next to neutrino, next to left-handed EMs, electron, muon, and tau, right? In a doublet of SU2 left. The representation theory is like this. Whoops, what happened? The representation theory is like this. These are leptons, right? So 1, 1. SU3 has to be 1. 2-dimensional, right? The doublet. Electric charge, a hypercharge, I just have to tell you what it is. It's -½ for this doublet. The right-handed E of M. Remember that there are no right-handed nu of M. This is lepton, right-handed, so not charged under SU2 left. Charge, hypercharge -1. Good?
This is only coupled to the U1 side. U1 part.
Sorry, say it again.
It only interacts with the U1 part.
Yes, yes, yes. Hypercharge. You only have hypercharge. Now, for the hadrons, I'm gonna define the following doublets. Again, these are the doublets, right? The left-handed ones. I'm gonna package the left-handed ones next to each other. The left-handed Majorana of ups and downs. I'm gonna package them as a SU2 left doublet. Here's the representation theory now. These guys are charged under strong and they transform as fundamental representation. So this is three-dimensional. They are, it's a doublet, SU2 doublet. So this is 2. And the hypercharge is 1,6. I also have the right-handed hadron Majoranas. The fact that they're right-handed, it means that the electroweak is 1, trivial representation. But these are fundamental, and their hypercharges are 2/3 and minus 1/3. Good. So the fact that there is one here, and one here is the reason that we call this SU2 left. Because all the ones that are projected to right are not charged under it. Right? These 2 and 3s and the rest you could just deduce based on basics of representation theory. These charges you have no way of deducing, right? Like it's given. Somebody tells you these are the numbers. At the moment, right? So is the particle content clear? All right. Now, here was I described everything in terms of wild fermions, right? But these guys have their the left, okay. Every Majorana, a left-handed Majorana fermion has a left-handed piece, and the right-handed piece is just epsilon of the left-handed star, right? So I know that the notation could be confusing, but now I can package PR of nu of m next to PR of E of m, right? These are leptons, so 1 is representation. But under SU2 left, they transform as 2. Right? Because these were the left-handed Majoranas. Half. Notice that if I was formulating standard model using while notation, I wouldn't have needed this slide at all. Right? Everything, I was just talking only while. Turns out that introducing this, like this new slide is helpful. It helps with calculation. But there's no new content to it. The important part is that that for your Majoranas, the top guy and the bottom part are related in this form. Right? So if this is transforming as fundamental of SU2, right? If this is 2, this is 2. Right? Now, there's one subtlety that comes up when you talk about the representations of the hadrons, the under SU3 color, that these right-handed pieces of the left-handed Majorana transform as 3 bar anti-fundament. Good. Notice that the charges flip as well. Minus half. Right? -1 + 1. 6 minus 6. 2/3 minus 2/3 minus 1/3. What is this pointing to? Remember that we said that there's CPT symmetry, right? Charge parity time reversal. So we had an extended discussion of that. Anyway. Here we're talking about a map that sends the left-handed wile to the right, just swaps left and right. Right? Okay. Said differently, these are particle antiparticles. Right? So these are the antiparticles of what I just described. Good. Now, we could also write down these things for the gauge boson, representation theory statement for a gauge boson. The gluons are transforming at 810, right? 8 adjoint. This is obvious. This is also obvious. This guy is 130, 110. Good. All right. So that's it. These are all the particles that we have. We have 6 leptons, 6 hadrons. I have 8 gluons. I have 3 W bosons, and I have 1 hypercharged gauge boson. Right? There's 1 extra particle. There's 1 more, and that's Higgs. Higgs is a complex scalar field. So it's so far everything I described was spin 1 or spin half. Right? Spin half or spin 1. That's all I described. There is 1 mode that's spin 0. It's a complex scalar field, Higgs field. And it transforms in the following representation. It does not talk through strong force. It transforms as a doublet in electroweak. So it takes part in electroweak, and it has SU2 left, and it has hypercharge minus half. Now, it's this complex scalar field that requires a Webb breaking spontaneous symmetry, leading to spontaneous symmetry breaking of SU2 left times U1, UY1 down to U electromagnetic 1. But this U electromagnetic 1 is not this. This is another subgroup. I'm going to tell you in a second what that subgroup is. Okay, any questions about matter content? I have to speed up.
Small question.
Yeah.
The fact that the Higgs field doesn't couple to the SU3 part is the reason why the gluons are massless, right?
Yes, absolutely.
That's it.
Very good. Absolutely. Otherwise, we would have called it electroweak symmetry breaking. Would have called it SU3 times. I don't know what we would call it. So to just orient ourselves, I'm gonna write down the gauge transform. It's a gauge theory, right? It's a gauge theory with gauge group SU3C times SU2 left times U1Y hypercharge. The transformation under U1 hypercharge is like this. So the gauge field associated to U1 hypercharge transforms as del mu under gauge transformation, del mu of omega 1 of x. The transformation of the under SU2 left is del mu of omega 2a of x. A runs from 1 to 3. And then this is the adjoint representation, right? This is the origin of interactions. For SU3, I have 8 of these guys, omega a's, and then there are these FABCs associated with SU3. To be more explicit, the fermions, I also have to tell you the representations of the fermions. I already did. But let me remind you of how it works. Fermions are in the doublet, two-dimensional E-reps of SU2 left. So the T's, oops, I did not write it. So TA's are half tau A's. Maybe I want to put the labels down here. And tau 1, tau 2, tau 3 are the Paulos. They also, the hadrons are in fundamental representation of SU3 charge or anti-fundamental. The representation matrices are T alphas. These are the Gilman matrices. Half of lambda alpha, alpha runs from 1 to 8. These are three-dimensional, these are fundamental representation of SQ3. Here are the Gilman matrices. They're nothing really fancy, right? They look like you put a copy of these following matrices on this block. You try to do a similar thing down here. And then you have this final guy like this. These guys all have zero trace. Why? Because it's SQ3. Okay. Now the gauge transformation of fermions. Let's take our oh God, I can't talk. LMs, right? There would be the left-handed part, there would be the right-handed part for LMs. The left-handed part, these are leptons, right? They transform as trivially under color. So there's no omega-3 alphas here. Minus half means that this is minus I over 2 omega 1 of x. Right? And then this 2 means that it transforms under fundamental rep. The right-handed part is 1, 2, half. This is the right-handed part of the left-hand. Hopefully you remember that, Majorana, right? That's a little bit, it takes some getting used to. It might seem a little bit annoying that I'm not using the Weil notation, but it's actually a huge plus. It saves a lot, it simplifies a lot of calculations. Now, the thing to notice for the right side is that the right-handed component is that this is now hypercharged half. It was minus half before, right? And this is still 2. The same for E of M, 1, 1, 1, 1, 1, minus 1. So this is only hypercharge, right? This is the right-handed Majorana associated with electron, muon, and tau. Now we get to our hadrons. The left-handed part of this guy, Q of M, is transforming under 3, 2, 6. 6 is hypercharged, so hence I over 6 omega 1. This is fundamental. This is what it is, and then this is guy is as it should be. Right? Now this part, the right-handed side of it is 3 bar 2 minus 6. So minus 6, 2, 3 bar. And then del UM is like the rest of it you could figure out, right? So antiparticle, particle, antiparticle, particle, blah, blah, blah. Right? So that, yeah.
Is it, notice that the left-handed coefficient, the left-hand part, right-hand parts are complex conjugates of each other.
Yeah,
That's intentional, right?
Yeah, these are the Majoranas. These are the Majoranas. I'm packaging everything in terms of Majoranas. So the point of Majorana is that you want the particles to come with the antiparticle. If I use Weil notation, I lose that.
One quick question. Like we can see when you look in the left-handed and the right-handed part, like if they're complex conjugate of each other, like 3 becomes 3 bar, but we can see that for the
So 2, 2 does not become 2 bar. Why is 2 not 2 bar? That's something we discuss in detail in the representation of your SU2. It's SU2 sigma. Think about that. All right. So okay, I gotta speed up. I'm almost done. So this is what I'm gonna say at the end. I said this several times. We are presenting standard model right after spontaneous symmetry breaking of gauge theories because standard model is an example of that. So this is electroweak symmetry breaking. We have a complex Higgs field. It's this complex scalar field that is charged under, it has a hypercharge and it has the electroweak charges, right? This is a representation under SU2 left times U1 of Y. It requires a VEV, and it breaks this guy down to U of E of M. Now, the electric charge is the third component of the SU2 left charge plus the hypercharge. So if this was just Y, UEM would have been U hypercharge, but it's not. So the spontaneous symmetry breaking is a little bit more involved. Good. So do not make this mistake. Photon is not a particle in the before spontaneous symmetry breaking, electroweak symmetry breaking. Photon is not a particle in the spectrum of Samuel at all. It's a Goldstone boson. No, I did not say that. It's not a Goldstone boson. All right, so that was it. Let me just summarize. We went through what did we go through? Oh, spontaneous symmetry breaking, quantization of spontaneous symmetry breaking gauge theories. We very quickly went through that, and we saw that the key feature was that there was a mixing term that we got rid of using gauge fixing, using smart choice of gauge fixing, but that smart choice of gauge fixing gave us came at the cost of introducing a whole bunch of ghost fields, and the ghost, because of the structure of it, they even in the abelian theory they couple to Higgs, right? So in the non-abelian theory they couple to Higgs and the gauge field, right? All right. Then we started our discussion of standard model particle physics. We said that we have the particles. The gauge group is SU3 collar times SU2 left times U1 hypercharge. That gives you 8 gluons, 3 W bosons, and a B boson, right? 1 boson for hypercharge. Those are spin 1 particles. The spin half particle content was 6 leptons. By definition, they do not take part. These are spin half particles that do not take part in strong interactions. And 6 hadrons, right? They come in generations like this. Then we organize our representations here in the following way. We said that we're going to take a Dirac spinner, split it into 2 Majoranas, left-handed Majoranas and right-handed Majoranas. But you know that the left-handed Majorana has the left-handed mode, which is a wild mode, and its right-handed part is this antiparticle. Just like the same thing above, copied downstairs, multiplied by epsilon and star. And then the other way around for the right-handed one. The point of this was that only the left-handed Majoranas were coupled to SU2 left, hence SU2 left, right? And the representation theory was basically like this. Well, this part is obvious, right? The transform in adjoint, that's all that matters, right? And this is all you need to know about it. For the leptons, the left-handed parts transform as fundamental of SU2, and the hypercharge is minus half. The right-handed part is trivial under SU2 because it's right-handed, and hypercharge is -1. For hadrons, the left-handed part is fundamental of both SU3 and SU2 left. Hypercharge is 6. The right-handed part of the up and down are, of course, trivial under SU2 left, and they're fundamental, and their charges are 2/3 and -1/3 hypercharge. Good. That's the particle content. I said there's one last particle, which is scalar field, the only scalar field in standard model particle physics, the only scalar field we've ever detected in nature, fundamental field, and it transforms under. It does not take part in strong interaction, so it's 1 for SU3 color. For SU2 left is 2, it's fundamental, and its hypercharge is
-half.
-1/2. All right. Thank you so much. Any questions?
In the element matrices, we